Our last lesson that should be Regents Review is about what happens if you put a current loop inside a magnetic field. So not just a single line carrying current, but a loop of current. So this black line I have here is representing my current loop. So let's say for whatever reason we have a potential difference. There's a current going around in this loop in kind of this direction. So if you were looking from above, you'd say the current was clockwise. So current going here, current going here, current going here. And I've put it between two poles, magnetic poles, a north and a south. So there's a magnetic field in this region that the loop is in, which is pointing from the North Pole to the South Pole. Before you leave angry comments saying that, of course, you can't have magnetic monopoles, these are somehow connected. I don't know, they're horseshoe magnet or something. See? There, complete magnet. Let's figure out what's going to happen to this loop in the magnetic field using the right-hand rule 4 times. And we're going to figure out the direction of the forces on these 4 segments of my current loop. Okay, the segment in the back that I'm highlighting, if I look at that, the direction of the current here is parallel to the direction of the field, so the force on this particular one is 0. So let me call that section 1, and F1 is 0. Similarly, if I look at the one down here that I'm highlighting, the one sort of in the front of the loop, the direction of the current is anti-parallel to the direction of the field. So once again, the force on this section is going to be 0. So I'll say F3 is 0. Okay, now if I look at the remaining 2 sides, so I'll call this one section 2, F2. To get F2, I'm going to have to use the right-hand rule. So my current is pointing sort of out of the page. So I point my fingers pointing out of the page, and I curl my fingers to the right, and that gives me a thumbs up. So my force on this section, F2, is pointing straight upwards. And similarly, if I do it on this section, call it F4, then using the right-hand rule once again, pointing my fingers, oops, that somehow became a frictional force, pointing my fingers into the page and then curling my fingers to the right, I get a thumbs down. So the force on this segment to the left is downwards. You might stop now and say, well, of course the net force on the loop is 0, nothing's going to happen. The net force on the loop is 0, which means it will not move. There will be no translational acceleration, but we have torques and we have sort of this axis of rotation in the line I drew right here. So what's going to happen is that this loop is going to start rotating this way. One way of looking at that direction is to say that the normal to the loop, which I can get by sort of imagining the plane of the loop as in the page here. If I imagine this is the plane of the loop, then the normal to the loop, which I can draw as an arrow pointing perpendicular to that, the normal is going to be pointing straight up out of the page. And what we can say is that the normal of the loop tends to rotate until it's parallel to the magnetic field. At this point, we're going to evaluate just how much that torque is. To do that, let me give you some dimensions for the loop. So let's say this long side on which you have force 2 or force 4, let's say that has length lowercase a, and let's say this shorter dimension, the one that's currently parallel to the field, has length b. And now let's look at this picture from the side. So I've redrawn the current loop an instant later after it started rotating, and we're looking right at the short side, the one that didn't have any force on it earlier. I've redrawn the normal loop as the normal to the loop from where it is, and you're now going to notice that the normal makes an angle with the magnetic field. I'll call that angle phi, and let's calculate just how much the torque is on this loop at this instant. Of course, the torque is only acting on these 2 wire segments that I can't quite see. It's the ones that are coming into the page and going out of the page. So let's start with the one that is where the current is coming out of the page, so that's F2, and let's calculate the torque on F2. Of course, by definition, torque is equal to R cross F. So let's figure out what F2 is. R clearly is going to be B over 2. Because that's how far F2 is from my axis of rotation. Here's my axis of rotation. And I'm going to do cross product F2, F2, I can just do ILB. B by definition here, well, I gave you B, but L by definition is the length of that segment on which the force F2 is acting, and that has length A. So what I have is B over 2 cross I little a large B, where that one stands for the magnetic field. To take the cross product, we want to figure out what component of the force is perpendicular to the lever arm. So if I extend my lever arm, you can prove very easily this angle is also phi. Cutting off the perpendicular part of this will give you a sine of phi. So that means overall the torque on that segment F2 is going to be I a b, little b, big B over 2 times sine of angle phi. I can perform the same analysis on F4, and of course I'll get more or less the same result. I don't know why I'm saying more or less, I'll get the same result. So the torque on F4 is, wow, once again that became an F, is going to be I little a little b, big B over 2 times sine of phi. Since both force F2 and F4 tend to be rotating the loop in the same direction, then I can immediately find the net torque from these two by taking the sum, and that'll just give me I little a little b times the magnitude of the magnetic field times sine phi. Or if I notice, little a times little b is the area of the loop. It's going to be I times the area of the loop times the strength of the magnetic field times the sine of the angle that the normal makes with the magnetic field. Before we generalize this to more loops, I just want to remind you guys that there are two other sides here where I have F1 and F3, and I seem to be neglecting them, even though the force on these two is no longer going to be 0. So, for example, this one right here with length B is no longer parallel to the magnetic field. So I could use my right-hand rule here to determine the direction of the force on the side that I see pointing out. But if I do that, if I point my right hand in the direction of the current and I curl my fingers in the direction of the magnetic field, I find a force pointing straight out at me. I think I labeled that F3 earlier. So F3 is pointing straight out of the page at me. And if I did it on F1, which is sort of behind F3 and I can't really see, I would find that F1 is pointing into the page. So F1 and F3 do not tend to rotate the loop. If we had a sort of elastic loop, it might tend to spread it, but they don't contribute to the torque because there's no rotation. Lastly, I can generalize this to any kind of shape of current loop in a magnetic field, even one that has multiple loops, like what we call a solenoid. So in general, what I can say is, wow, that looks like a disaster. If I have n loops, then the overall torque, tau, is going to be n times the torque on one loop. So n is going to be, the torque is going to be n times the current times the area of that loop times the magnetic field times the sine of the angle made between the normal and the magnetic field. I didn't prove it, but this does work for geometries that are not rectangles, and it is actually pretty easily proved. But so for example, if you had a circular wire loop with a radius r, your torque of course would be n I pi little r squared b sine of the angle phi. Before I go, just have a really good spring break, guys, and I will see you after spring break.